Hi, everybody. As Moritz said, my name is Michele Doro. I'm from the University of Padova. And today I will speak about dark matter searches with IACTs. We will then focus on this part of the world of dark matter searches. I have to apologize for my voice. I'm coming out from a flu. I hope you can hear me well. Okay, let me go fast to the outline. I will dedicate some time to explaining the IACT, especially for the youngest one. I will apologize to the expert. And then I will focus on the reason why gamma rays are good dark matter probes and tell you some stories about past searches and the present and future. There is a session after me today, but there were interesting talks on Monday, the first day, which I reference here. So there will be some overlaps with these posters too and talks. So most of the material that is shown here was collected in a recent review that Moritz, Miguel Angel, Sanchez Conde, and I wrote for a book on world scientifics, which I propose you to have a look, and I put the link there because it includes not only massive particle dark matter, but also other fundamental physics topics in the field, like action-like particle, primordial black holes that were discussed in this conference, as well as tau neutrinos and magnetic monopoles. Many things that you can do with IACTs. Okay, and please, considering this a review, if you're expert, please provide feedback before the final submission to the book. Okay. Okay, so this first part is dedicated to a little bit of introduction to these techniques, imaging, atmospheric, Cherenkov telescope techniques, and its framework. Okay, I will give some basic information that will allow us to make some consideration afterwards. So let me quote here, first of all, Aharonian, who said recently that, and it's true, we had 3 revolutions in the gamma ray skies in 3 decades. We have the TeV revolution in the first year of the century, in which from 2 sources, as you see from the plots, we fastly came out to having 10 and then more, and then 100 and even more sources now. And we are ready for CTA, as I will explain afterward. This was unexpected, and it's really one revolution. It was followed a little bit contemporary, maybe, by the revolution at the GeV, okay, passing from the egret sky to the very peculiar Fermi-Lat sky, which we are all familiar with. But finally, recently, we're having another revolution in the PeV now, with LASSO and with future instruments to come. Okay, so it's really an amazing time for high energy gamma rays astronomical searches. Okay, so the IACTs, I don't want to say too much, but what is important to understand is that our event is a shower of particles in the atmosphere here, coming from primary gamma rays. This happens at about 10 to 20 kilometers above the ground. And then we do not see the particles with IACTs, which we see just this blue flash of light, okay, which illuminates a circle in the ground of 120 meters. This is our effective area, okay? So we have kind of a very big detector, because any place you put the detector here, you see the shower. And the event for us is just an ellipse in the camera, from which we can determine the energy and the direction, and of course the time of the shower itself, okay? So the primary shower is composed of just electrons and other gamma rays, and the electrons produce Cherenkov light because they travel faster than the speed of light in the medium, okay? So this happens at 10 kilometers. And that's why the image is kind of extended for us, and we cannot reach that good angular resolution as optical telescope. Okay, so that's the starting point for us for the reconstruction, and what we have is that we not only have gamma rays, but we have really an ample background from this observation point of view. Let's say that for one gamma ray, we have kind of 100 or 1,000 protons mostly, okay, which constitute for most of our searches a background. So a proton is something like, also creates, an atmospheric shower, as you can see from this image. You have mostly proton, alpha particle, iron, they enter into the atmosphere. And what you have now is a more complex shower. You see that you have pions, and you have, among the pions, you have the neutral pions, which in turn emit electromagnetic shower, which are very similar to these gamma rays ones, okay? So in some cases, the signature are very similar. Luckily, this complex shape is reflected into the image. Here you have on the right, for example, a simulation of what is a gamma ray shower, okay? So very direct. A proton is more extended, and an ion shower is really much extended, okay? We see this in the images of the shower, like for example, this one. On the left, you see an image of the gamma rays, and on the right, you see an image of a proton, which is kind of more, less, so to say, geometrically contained. This is the first way in which we can separate the signal from the background, and we can do this well with a, we can reduce to a factor 100, 500, but what's important to understand is that at the end of the day, we will always have an irreducible background, which is kind of conspicuous in this technique. Okay, so on the left plot, I show you an example of what is our detection plot. We have here an angle theta, which is the angular separation from the source. We have here the number of events, and this line here tells us where the signal region here is, okay? So in this case, you see the background is here, the signal is there, we have a strong signal, that's a crab, we have 125 statistical deviation from the background, but most of the time, this is the case, okay? This is a weaker signal in which our signal region is there. And this is the amount of background that we cannot get rid of, okay? So all our significance is obtained on top of an irreducible background. Okay, so the major IACTs in the world, there are many, but three are, so to say, major in size. One is Veritas in the United States. It's composed of 4 telescopes, as you see here. And you see that the size of these 4 telescopes is 12 meters in diameter. It's operating since 2007, okay? MAGIC is operating in the Canary Island here in La Palma from 2004, and is composed of a slightly larger telescope than Veritas, 17 meters, but just 2, okay? And then we have a big installation in Namibia called HES, which is composed of 4 telescopes of 12 meters plus one big one of 28 meters, okay? These are not the only ones. There are also many other Cherenkov installations in the world. You can check Taiga, Macy in India, and so on, okay? But these are those really focused on gamma ray astronomy and producing most of the result now. These 2 are in the Northern Hemisphere, as you see. S is the only one in the Southern Hemisphere, okay? So IACTs are not the only detectors. I think I have to go a little bit faster. We are in the TeV, but I want to tell you that for researchers that we have friends in the MEV, GV, Fermi, that will be discussed. We have Hawk and Swigo in the TeV, slightly larger energies, and then installation like Auger, okay? And this is our field. I want to focus to tell you that we have different capabilities, okay? If you compare the sensitivity here, okay, for example, this is MAGIC, and this is Fermi, you see differences, and this is LASSO, you see differences in the sensitivity reached throughout the energy spectrum, okay? But the sensitivity is not the only thing, okay, that matters. You have to think that the integration time is different. So gamma ray telescope, you see here, this is the sensitivity that I was showing before. But if you compare the sensitivity over time, so LAT, this is 10 years, HES, this is 100 hours, or CTA. If you compare this in time, is different because Fermi-LAT needs to integrate because of a small effective area. Instruments like IACTs, like CTA, have this wide area, and then they can detect very well phenomena, transient phenomena like 1-minute flares, much better than Fermi. Okay, so in short, any instrument has its own performance, and when you're looking for dark matter, you have to consider this. For example, the energy resolution is pretty important for us, because if you see here a simulation of spectrum, the dotted lines are what you expect, and with the energy resolution is what you have when you smear with the energy resolution. So any signature in the spectrum will be smeared by this. Okay, let me skip the angular resolution. The other important point is the field of view when we consider such experiment, because we cannot really monitor the full sky with IACTs. We mostly focus on small region in the sky of few degrees square. Okay, so we have to choose where we point the telescope. And of course, IACTs observe light, and so they can just work at night, okay, compared to other instruments. So our duty cycle is kind of 1,000 hours per year. Okay, so why gamma rays are important as probe for dark matter? We have to remember this, and there are a few reasons that I want to highlight here. Well, first of all, they are predicted by many theories of dark matter. This is a beautiful plot by TeV. We don't know which is the actual dark matter model, and then we really have to try at the moment to investigate as many models as we can with the instrument that we can build. Not only this, we're working into, as you know, as it was shown in this conference, the search is made really by many experiments, and it's important to remember that, as was shown here, there are places in the parameter space like this one, which will be excluded, this one, which will be, are not excludable by other means, but indirect detection, okay? So kind of these searches are complementary, and it's important to pursue all of them. The third reason is that we know where to point. We have a model. That tells us where dark matter is expected. And in one model, we have several targets, galactic ones, extragalactic ones. So we are not shooting in the dark in a certain sense. We know where we expect dark matter from gravitational mismatches. And finally, not less important, is that the dark matter signatures we expect is universal. So once we get one, we also know that in the other places in the world, in the universe, we will have the same spectrum. This will be a really important confirmation of once we detect dark matter, what is dark matter? It's not so trivial to say. Okay, and plus we have signatures in the dark matter spectra, like these cutoffs here, which do not resemble astrophysical source. So once we get it, we should have a very clear identification of dark matter. Okay, so let me start the part now with some stories of IACTs. I hope these are not ghost stories or tales of terror, as this book suggests. But let me go straight on. Okay, these formulas we know already. We know what's important to underline again is that the flux we expect at the detector is made by a particle and an astroparticle part. Okay, so the particle is the nature of dark matter, which we don't know. But the astroparticle term here depends on the density of dark matter, which is something that we can try and understand by astronomical observation. The point is that, well, if we have detection, that's okay. We are happy. If we have a non-detection, any of all our limits depends on the accuracy of the knowledge that we have on the astrophysical factor. So for us, this, so to say, external information is really an important factor, as I will try to explain. Okay, so let me do some history. We had, maybe not everybody remember that we have a TeV dark matter claim back in 2006, which boosted many information. This came from the Cactus IACT, well, not imaging, ACT, located in California. It's a solar power plant converted into a telescope. And there was this claim during a conference, it was not published in the end, that there was a detection in the direction of Draco, okay? I didn't read this paper because it's too expensive, but there is a paper by Bergstrom, Hooper, another in 2006 that was discussing this, okay? So there was a claim back then about a signature at 500 GeV dark matter, okay? This prompted really a lot of searches in all the other instruments that were built and started to take data at the time, has Magic and Veritas. And as you see here, we took data on dwarf galaxies and the Milky Way center, 7 hours, 7 hours, 18 hours, these are the hours, on Draco, which is one of the best targets. We had really great expectation back then. I was there. And we started this research, okay? Well, after 15 years of observation from these 4 targets, we now reach this complete list of observation, which is reported in this paper, that in this review that I was saying. And as this bush says, we did not detect dark matter, you would have known it. Okay, so I'll try in the minutes that I have to really go into this table and try to discuss the targets of observation that we had. Okay, so the obvious first target is the Galactic Center. Okay, the Galactic Center is best seen by HESS. And is located, because HESS is located in the southern hemisphere, okay? I don't know why the image does not appear, but anyhow, this is an image, a zoom of the image in gamma rays, TeV gamma rays of the Galactic Center. And as you see, it's a very crowded region in gamma rays, in TeV gamma rays, which HESS is observing for many years now. So you can do a lot of astrophysics here, but you can even look for dark matter. What's complicated is that you have to model very well the background, okay? You have really to do this kind of Pac-Man shapes in order to determine where your background is. As you remember from my introduction, we have this reducible background. We have to estimate it very well in order to look for a signal on top of the background, okay? So I recommend you this review here of Mathieu de Narrois, which explains how we do this for IACTs. The second problem in the Galactic Center is that there is a lot of things happening there. So if you want to look for this dark matter profile, we call J profile, due to the baryons feedback, we have uncertainties. So that's a plot with the offset angle. And this is the density of dark matter here, okay? And you see that we have 2 models. One is very flat, so-called core, and one is very cuspy, okay? An ASTO and chord. And that's the J factor, more or less, that we need to have in order to claim our limits. And you see that we have strong differences at the moment. Okay, so during the time we have observed the Galactic Center a lot, and the deepest observation is with HESS. You see here, especially in the recent year, they have really gathered a lot of data, 254, and recently there was a tight CRC analysis for 500 hours, okay? I will show you here the results from the 254 hours. These are 2 channels, tau tau and BB bar. This is the thermal relic density. Below this place, this part here, you expect to see dark matter. This is the mass and this is the cross section. And you see that we are kind of touching this space, parameter space with the Galactic Center, okay? These limits are valid for the ASTO profile, okay, not for the core profile, but are pretty strong, and there's the strongest constraint so far with this kind of techniques. One should see that for the Galactic Center, we can also expect some decay signals, and there is an interesting study by Magic, presented again at the ICRC by Daniele Minci, and in which you focus, basically, from the northern hemisphere, the Galactic Center goes very, very down, okay? It's not very high in the sky. So you see it moving, okay? Moving in the sky. And if you check in different position in the sky, you have a good estimation of the background, and you can do pretty interesting searches for decaying dark matter, okay? So that's a limit here, shown in 2019, okay? And you see that we can reach limits of 10 to the 26 second. So now these are lower limit for dark matter decay, and in just 20 hours of observation, okay? A big field of research is that connected to the satellite galaxies. Let me remember that if you believe dark matter is in the Galactic Center, you also expect dark matter clamps around the Milky Way halo, okay? So we're focusing now here on these clamps of dark matter. And as you see here, this is a simulation of dark matter. You expect to have these clamps and we can kind of distinguish them in two classes. One is we call the visible clumps, okay, in which galaxies has formed. And we heard in this conference, they are dubbed dwarf spheroidal galaxies and dwarf irregular galaxies. We also may have places in which we have clumps of dark matter, but there is no matter there, okay, no baryonic matter, so no visible counterpart. We can call these dark subhalos, okay? We'll talk about these two in the next slides. Now, these targets are interesting because they are very clean. You do not expect to have as much background as for the Galactic Center, because these dwarf satellites galaxies are kind of isolated and they are not so active anymore, okay? So any astrophysical emission is not strong. We have a pretty good list of them. This is a dwarf candidate list by Francesco Saturni, kind of 30-40 now. You detect them with photometric instrument, but in order to, as an agglomerate, as a cluster of stars, gravitationally bounded, what you have to do afterwards to determine the dark matter content is to study the velocity dispersion. The first one were discovered, well, most of the first one in the first decade of this century. Now we are building instruments that really will make us able to detect mostly all of them, or probably all of them. See also Anna Genina's talk. So we will have a complete list of these guys in the future. The problem of these guys is that if you take the most brilliant one, like Draco, for example, this is a plot in which you have the velocity dispersion for the stars, okay? So you have stellar population, but this underlined in red is the stellar population of Draco, and these are foreground stars from the direction. You have to identify the stars that belong to the dwarf. So for the classical dwarf, the bright ones, you have this situation. For the new ones, they're really dim, okay? So you can expect very few stars. So if you compare the two, okay, really what you have to claim dark matter is just by this peak of 10, 20 stars compared to this signal here. So the problematic is to define spurious member like binaries or this foreground stellar population that I was talking about. And all these affect the accuracy of the result. And these tell us how much dark matter is there. We don't know it very precisely. That's why there are many studies that compare J factor. You see here some comparison that we are doing for CTA. And for each target, I didn't put the name on purpose, you have fluctuation, you have targets that are better known, and others in which this J factor, the dark matter density, say, fluctuates a lot. And from this depends our limit, okay? So that's an important point for us. What's good is that at least the core cusp difference, this one that I described for the Galactic Center, is not so intense for dwarf as we show in the past year, because they are more compact, more far away, and so this effect is less strong. So there is an uncertainty, internal ones, but not affected by the core cusp difference, which was discussed in this conference. Okay, so that's the list that we have of target. And you see here, 7 hours, this is the number of hours, sorry. So 50, 18, 60. These telescopes have devoted, okay, from 3 to 160 hours on each target. More than 1,000 hours in total in this decade. And if you remember that we have 1,000 hours per year of observation, this is really a lot. IACT's made a good effort, a huge effort to detect these guys. And the list is very large on where we pointed our telescopes. Okay, if I have to choose one result, I take this. This is a deep observation by Magic on Segway. Segway is one of the best candidates. You see here the usual plot of cross-section limit versus the mass. You see here for one channel, the Fermi limit and the Galactic Center limits that I showed you before. and that's Segbe 1, okay? So the dwarf limit. So it's 1 order or 2 of magnitude farther away, but as you remember, this is kind of different robustness level than this one, which depend just on the Enasto profile. Okay, the message here is that these results are anyhow the strongest compared to our instruments in the field above a certain mass. So if you check here, above 600 GeV or few TeVs, IACT's limits provide the strongest constraint on the parameter space. I told you that some of these guys can be dark, okay? So if not enough material has fallen in the light was not switched on. So this is how you would see it in optical, in gamma rays, sorry. But if you look at them in optical, here in the position, you don't see anything. So the problem for my IACTs is, where do we point the telescope? We have a small field of view, where do we point to see them, okay? On the other hand, we expect a pretty large number of them from simulation, okay? I just put one reference here, but there are many that predict a huge number of clamps. So where do you point the telescope? One way was to point for unknown gamma rays emitter. And we have, as you see here, this is Fermi catalogs. You see that we have, of the full list, we have a lot of unidentified sources. Like roughly 10–30% of the sources are unassociated. So they are kind of candidates to be dark matter, okay? Not all of them. So if you really select among these unidentified by steadiness, by spectral shape, by brightness, by association, you will end up with few valid candidates, and that's what was done. We pointed at these guys here along the years from 2010 to recently. There are many publications that try to look for dark matter in these guys, as it's obvious to do. The problem of this is that, well, if you see it, that's fine. If you do not detect any signal there, you're not sure in the first place that it was a dark matter clamp. So you cannot really put limits on the single source dark matter wise. You have to assume the astrophysical factor that you don't know what it is. Okay, pretty well. There are other targets in the galaxies. I will have to be a little bit fast here, like in the intermediate mass black holes, or globular cluster, or even other galaxies. Also extragalactic, in which you can look for dark matter. So intermediate mass black holes are predicted object between 30 and 10 to the 5 solar masses, this intermediate mass, which may be wandering in the halo. Again, they can be dark as these these dark lamps. So you don't see it in all the wavelengths, not necessarily. And the dark matter density around these guys can be kind of boosted by the absence of matter. And so you can expect a strong signal from these guys, but again, you don't know where they are. So you do, if you have to point the telescope, you do searches like it was done on Fermi, unidentified targets. And you have globular cluster, but there we really don't know how much, we have more uncertainties on how much dark matter is, if at all, in globular clusters. Okay, so for example, if you look for M15, you see that this is in a Hess paper. You see that according to the model, this is one model, this is another model, you have pretty strong uncertainties on how much dark matter is there, and this affects totally your result. Okay, another interesting target for dark matter searches is the galaxy clusters. Okay, galaxy clusters are, there are many around, and are these very massive gravitationally bound targets, which contains many galaxies. And because of this gravitational pull toward the center, we expect a lot of dark matter at the center. The problem is that they are very, very far away. Okay, so any dark matter signature from these far distances is, reduced just by distances. You have to, the modeling of dark matter in galaxy cluster is a little bit complicated by the fact that you have a lot of structures there in dark matter, and all these structures and substructures, they can contribute to the signal itself that you see. This is so-called substructure boost effect, and it can be something by 5 to 20 times the J factor of the smooth halo. The smooth halo is the halo that do not consider these subclumps. So you see here, there was an attempt, many, I just quote one here by Miguel Angel, of defining the best targets, the best cluster for observation with IACTs. And this is the list with a J factor and with a tentative rank, okay? The best one is Virgo, as you say here. The second one is Fornax. The problem is that if you look at the extension of these guys, it's of the order of degrees, and this is pretty much for the field of view of IACTs, which is of the same order. Okay, so we cannot really find observing that targets very easily with our telescope. This will be changed with CTA, as I will tell you afterwards. But at the moment, these are pretty hard target to see. Okay, they are not that competitive for the annihilating dark matter, but surely they are beautiful targets for decaying dark matter, as I will show you here. Okay, so let me just focus on two results. This on the left is the limits from Hess observation on Fornax. Okay, this is Fermi, the Fermi lines. You may remember this. This is even below here is the parameter space, and these limits are very high, 10 to the 21. Okay, but you have to remember that these come from just 14 hours. Okay, so it was not a very deep observation. As we saw, we need hundreds of hours on this target. MAGIC focused on Perseus in the northern hemisphere, Perseus galaxy cluster, for 200 hours, it focused only on decaying dark matter, and you see that the limits are again these 10 to the 26 seconds, which are pretty good constraints. Okay, but Perseus, for its nature, is not interesting target for annihilating dark matter as other targets. Okay, we also have the possibilities to see lines. Now, lines are, dark matter lines are everywhere. Of course, they should be concentrated on the places in which you expect to have more dark matter. What's interesting about this line is that, as I said before, we do not expect confusion with astrophysical lines because of their position. A problem that we have is that we have to, in order to detect them, not only we have to have sensitivity, but also energy resolution. And as you remember this plot, if you have one line like this one, gamma gamma, if you have an energy resolution of 50%, this line is not a line anymore, okay? So we have to work on having very good energy resolution for these instruments in order to detect lines. But there are many papers about line searches. I put the list here, and the limits are also pretty good. I don't have here a comparison with Fermi, but we are competitive to Fermi for lines. Okay, so I have to hurry up. The summary so far from what was done in this 15, 20 years, it's maybe shown in this plot. Again, mass and cross-section, and mass and lifetime for decay and annihilating dark matter. This is where we aim to have dark matter, and this is Fermi. This is the Galactic Center limits best from Hess that was shown. This is our best result from dwarf, and this is our best result from galaxy clusters. Okay, you see that we are competitive with respect to Fermi above certain energy threshold, and also for decay dark matter, again above some certain energies, our results, IACT's results, are competitive to the best limits by Fermi. Okay, here. So we are kind of sensitive in the TeV part. So in the few minutes that I have, what lies ahead of us? Okay, chaos or order with this observation. So in 20 years, we did not detect it. What can be done now? Okay, it's not an easy question to answer, but let me tell you what we're doing now. The first things we're trying to do is to have more robust and more constraining result by combining observation. Okay, not only by IACTs, but it's possible if you build a clever likelihood which kind of have nuisance parameters for all the instrument features and focuses on the cross-section. You can combine results from Fermi, from Hess, Magic, and Veritas, from Hawk, as see here. And we are really combining now thousands of hours of observation, okay? So let me point you to these results from Armand et al. In the ICRC, past ICRC, in which we combine, so this is the combination of all limits. And so Fermi clearly determines these limits here, but above some certain energy, IACT starts to be contributing here, okay? And also here, this is the blue one, is the Fermi limit. For other channels, we contribute on the highest part here. The problem of this is that if you look into the details, the limits are dominated just by, not by the fact that we have many dwarf, but just by the one with the highest J factor, okay? So what we need to have for IACT is to have a very intense dark matter J factor dwarf to be able to put strong constraint, okay? The other point is looking for new targets, okay? So not only combining them, and we have more instruments now that are telling us something in order to be able to have this accuracy that I was talking to you before. So for the visible targets, we have Gaia, we have a spectroscopical instrument that can provide better insight on dwarf or provide new dwarf candidates, which is really important. We have to invest many hundreds of hours. We need to know where to point. For the visible one, that's it. For dark targets, so targets that are not visible in visible light, we can rely on Fermilat for these unidentified sources. Fermilat is increasing the exposure as the time goes by. We also have other players. We have Hawk, we have Lasso in the TeV. Who knows, if they spot them, we could point the position, reposition our telescope there, okay? Hawk and Lasso are full sky instrument. They can tell us where these guys are. Another field pretty interesting is that of stellar streams, because a galaxy, like a dwarf galaxy, can leave a stream like this in its passage in the Milky Way gravitational fields. And not only the stream itself can be originated by a dwarf, we just don't know where the dwarf is, but maybe the core of the dwarf is intense enough to be observable as to be a candidate of being a dwarf. Plus, we can have gaps. As you see here, there are gaps in these stellar streams, which may be due to the passage of an object here, a massive object that has stripped part of the star of these streams, okay? So if you remember, intermediate mass black holes or even dwarf themselves can be the reason for these gaps here. Okay, so we may have new candidates. It's hard for us to invest time, as I said already. And also we have a lot of archival data to analyze, and we are looking now, the focus has also shifted from massive dark matter particles to other candidates like axion-like particles and primordial black holes, which can pop up from data that we already took, okay? In order to invest more time, we need really juicy dark matter targets, okay? I'm close to the end. We're waiting for CTA to be built. CTA is our future. It's not 2-4 telescopes, as we said, but as you see here, many, like 25 telescopes in the Northern Hemisphere, in La Palma, and 90 telescopes in the Southern Hemisphere in Chile. And as you may understand, this will change our performance. We have many telescopes that will allow us to have a boost in sensitivity. Okay, this is our sensitivity in function of the energy. At the low energy, we will be sensitive where we are not now. We will be sensitive in the energy, TeV energies, where we do not have a reach now with Veritas and Magic and Hess. Plus, we will perform better in where we are working now. Okay. Okay, let me skip here. The energy resolution and angular resolution will be much better. And also we will have the possibility with CTA finally to sample big fraction of the sky by displacing the telescope. So we will see more sky than what we are observing now. This will allow us, for example, to detect this dark object by serendipity, okay, in our field of view. And that's a study here in which it is predicted that maybe one dwarf dark subhalo can appear in CTA field of view. Sorry that I have to, to be fast on this. And even if we do not observe this, because now we have a wider sky instrument, we can place constraining upper limit by non-observing these dark lamps that I was telling you before. CTA is investing time to present its dark matter reach. We have published the Galactic Center. You see here that we are now entering the parameter space, and many other projects are in preparation. Okay, so this is the plot that I showed you before, and this is CTA. Okay, so we are really now going for a factor of 100 better result than what we have now. Okay, so stay tuned for papers about CTA performance from dwarf, the Large Magellanic Cloud, and the galaxy cluster. I want to mention the last sentence here is that CTA will have a guest observation program that will be increasing during the time. Okay, so it will not a proprietary instrument, and all data will be not only released, but you will be able to allow to ask for observation time. Okay. This is really important because if you have ideas, CTA will probably be the good instrument to allow you to make a program. And we have, I want to advertise this Gamma Pi software that is the analysis software that is public also to analyze CTA data and gamma ray data. Okay, we have our first telescope built, and more are coming in these times. Okay, this is the LST in La Palma. Okay, so let me go to the conclusion. It's a 50-year-long journey. We have brought home that gamma rays are unique probe. I hope I convinced you, at least in the TeV part. IACTs played a role in this together with the other instrument in this field. Our limits are legacy because we do not, I mean, we will be sensitive in a region where other telescopes will not be. But as long as we have a small field of view, we really need to know where to point the telescope. Okay, so that's it, just an advertisement for an issue which tell us about the success of IACTs in the past 30 years. And with this, I want to thank you for listening.